Okay, next exercise 1.6. This one actually asks us something about an epsilon-minimal element, which I think is how you pronounce this, but I'm actually going to frequently abbreviate it as in-min, right? So an in-min element is formally defined as any element. So let's say y is in-min in Z if y is in Z, and if anything else, or if anything is in Y, then it must not be in Z. Now, this is, at least to me, because it's kind of my first time ever seeing anything like this, was initially kind of a confusing, interesting definition, and so I'd like to share how I have kind of wrapped my head around what this is and what it means. Well, for one thing, notice that being in Y implies not being in X. Well, that just means that being in Y implies not being in Z. Well, that's just the same thing as being disjoint, right? That's just saying that if you have anything in Y, then the set Z must be located somewhere else, so to speak. So this is just saying that the two sets are disjoint. So that's one comment to make. Let's look at some examples. Now, trivially, the empty set has no in-min element since it has no element at all. That's not very interesting. But the set of the empty set does have an in-min element, which I claim to be the empty set itself. First of all, the empty set is in it. That, of course, is true, but is technically something that you need to have for an element to be in-min in some other set. Okay, what else? Well, we know by vacuous quantification that for anything which is in the empty set, it must not be in this set, and I say again, this is due to vacuous quantification because the for all sentence is never satisfied. And so just like the argument that we typically give for the fact that the empty set is a subset of any set, that's just due to vacuous quantification over the elements of the empty set. Here too, vacuous quantification establishes the point, or the claim. Okay. Let's think of a more robust example, I suppose you could call it. Let's think of this set A, which is the set 1, 3, 7. I claim that 3 is not an in-min element. It is in the set, but there is something which is contained in 3 and also contained in A, namely the number 1. Recall that 3 is equal to the set 0, 1, 2, and so 1 is in 3. But also 1 is in A, look back at A, and there you have it. So 3 is not an in-min element of the set. However, I guess I should, mention that 1 is an in-min element of this set. And it's no coincidence that it's the smallest element if we use our intuitions about the numbers. In fact, that's exactly what this definition of in-min is supposed to represent when the set that we're dealing with is the natural numbers constructed in the way that we have. So, so this in-min definition on sets, if we restrict ourselves to the natural numbers that we have constructed, any set with an in-min element has that element as a least element, in our intuitive sense of a least element. So, the thing that's kind of interesting to me, and because I'm a novice at this, I don't really know the answer to it, I'd be curious if there is one, is if there is because this is a more general thing, this is a general concept that doesn't have to apply to the natural numbers, I wonder if there are any interesting uses of it outside of the realm of natural numbers. I suppose I could easily see it coming up in, say, the integers or other number sets, but, what about sets that are not the constructions of numbers that we know and love? Are there interesting uses of this concept elsewhere. I don't know. I'd be interested to hear.